I'm not solving, I have m equals to k equals to 1 here. I'm expecting the angular frequency of the solution to be 1. Omega should be 1 here. I didn't solve the unarbitrary spring mass problem. I just solved this specific, most boring one. If you're comparing back to a more general solution that you know, then yeah, there's things missing because I didn't solve the general one. Absolutely. Okay. So anyway, this is how to solve first-order differential equations in a nutshell. There is still some theory I should share with you. Fortunately, we still have a half hour of class, so. What's that? Oh, 15 minutes? Ah, yeah. I probably have another day devoted to applications, right? If I remember my schedule correctly. The other thing I should talk to you guys about is the geometry of, you know, these solutions, but I'll probably save that for Tuesday, I guess, after your quiz. Let's see here. Sorry, my hands just do that when I say the words quiz. Could you hit half the lights? That's good. Let's see here. So I have, well, let me talk about these things another day. I just want to talk to you about the existence and uniqueness here for a moment. I'll get to it eventually. It's at the end. I can make this. Come on. Here we go. So these are the existence and uniqueness theorems I just wanted to share with you before I forget. If f is continuous on a rectangle, all right, then at least one solution exists for this differential equation, dy dx equals to f of xy, at each point in R. Moreover, these solutions exist on all of R in the sense that they reach the edge of R. So what this is saying is that if we go about the trouble of solving a differential equation, dy dx equals to f of xy, right? And if that f is continuous, all right, on some rectangle R, if you find a point in the rectangle, any point, pick it, there will be a solution going through that, and the solution will continue at least to the edge of the box. It's pretty nice. So I mean, this is very comforting. If you have a function with differential equation with a continuous formula over there, you can be assured that solutions exist, right? Nothing about uniqueness here, right? At least one solution. Now, the next theorem concerns uniqueness. So suppose f is continuous on the rectangle, like you're saying, and we have this condition that partial f partial y at a point is non-zero. Okay? That condition is sufficient that it will give you a unique solution. So if I don't have that condition, I could have the situation like this. I could have this solution here, and I could have that solution here, and I might even have another one. I mean, I could have a bunch of solutions going through that one point, right? But if at this other point, let's say x naught y naught, I have the condition that partial f partial y at x naught y naught is not 0, that says that there's just one solution that flows through that point. It's unique. So given an initial condition of that point, you kind of know what's going to happen, right? If your initial condition is this point, I don't know what's going to happen. So here's an example of a differential equation that has a failure, so to speak, of uniqueness. This is dy dx is equal to 2 times square root of y. So here, if you calculate partial f partial y, you get 1 over the square root of y, which misbehaves at 0, right? The differential equation is defined at 0, though, right? Like, can you put y equals to 0 in here? Sure, no problem. And so there's some really amazing plotting tools for you guys. You can look at differential equations in terms of their direction fields or slope fields. So this is, I've created this using the pplane tool, which I'll get out here in just a second, but these dots are pretty neat. These are where the domain of the, like this basically means the differential equation doesn't even make sense in here, right? Because you feed it the square root of a negative number, you get complex, and they know that's not a prerequisite for this course, so they just make it red. But you can see what's going on here. Like you pick any point here, there's always the y equals 0 solution, and there's another one that lifts up off. I can't say words. Words are not coming out of my mouth. Ugh. There's these parabolic solutions, these guys. But that's not usually, I mean, like most often the case, we actually have a unique solution through each point. If you go back and study the geometry of the problems we've looked at today, you'll find very, very beautiful pictures. See if I can do it. So in my, down here eventually, links to websites to do the math for you. There is in here somewhere, number 13. This one hopefully will work. Haha. Turn the light on for a second. I actually need to work something out so I can explain what this means. So we've been solving things of the form dy dx equals to, say, f of xy, right? But suppose that this actually has the form, you know, h of xy over like g of xy or something, right? This is, and I'll explain this in more detail another day, but I just want to, since I got this out, I want to show you it. Basically, we can trade this first order differential equation without time for a pair of differential equations in time. Now, we're adding something there, but basically dx dt equals to g, and dy dt equals to h. I mean, this much I can say. Solutions to this system parameterize solutions to star. All right. So let's start out with a basic example. I think this was one of the ones we worked out last class, the circle one. What was it? It was dy dx equals to, what was it? Dy dx equal to minus x over y? All right. X over y. That's good. Now, so I'm saying that this, you could, if you wanted to find parameterizations of the solution set to this, which by the way are circles, right? You could solve this system of differential equations. You can solve dx dt equal to what? Y, right? And dy dt equal to minus x. And these kinds of simple, these are called, it's called an autonomous system of differential equation. Autonomous just means there's no time dependence. There's no explicit time dependence here, and it's homogeneous in a sense that I'll make more rigorous as we go on. But you can actually plug these into here and look at it. And so it's a pretty simple matter. I mean, if you think about pretty much any differential equation, you can always do this stupid trick by just saying, you could always do this, right? You could look at dy dx equal to f and just say, well, f is f over 1. And so you could solve like dy dt equal to f and dx dt equal to So like this universal p-plane hack. See, I can read. I've been reading Yahoo enough to know that we call everything a hack now. So there you go. It's how to hack p-plane. Anyway, so getting back to my more interesting example, dx dt equal to y. And now this is I think this is actually in MATLAB, which you guys know how to run on machines. I don't have it. And here you go. Now, there's something else here that's not present in this differential equation, right? Like dy dx equals to minus x over y. Are the solutions counterclockwise or clockwise circles? Yes. There is no sense of orientation in the solution set. We just get x squared plus y squared equals to a constant. They're circles. But this is oriented. So that's one of the things. When you go to the corresponding system, you're building an orientation into it. You can't help but do it. So you can see the arrows, right? And you click on it, and it plots solutions for you, just like that. Isn't that beautiful? Now, what would happen if instead of doing x, what if I put the minus on the y, and I put the plus on the x? What happens then? So these are what? These are clockwise, right? Counterclockwise. So that's the choice of sign will determine orientation. Yeah. What is a differential equation we solved earlier today? What was it? What was that first one we did? dy dx? Was it x plus y minus 6? Is that right? Squared? All right. Let's try that one on. Oh, well, let's see if it can handle ASCII. I don't know about this. I may be getting too greedy here with just writing that out. I might have to square it. Somebody be squaring it while I try to be lazy. Oh, minus 6. Huh, worked. See those tangents? So you can actually see what we found actually looks like. Actually, you can look at p-plane for differential equations you can't even start to do the math on, right? Suppose you come up with a model in something you're analyzing. You can study what the solutions look like even if you can't hack through the calculus of it. You can gain numerical intuition about what you're doing using p-plane. What's another one we solved today? dy dx equal what? Oh, that one. Let's try it. Y over x plus 1 divided by... You know, I don't know if this stuff... Well, it's built over MATLAB, but MATLAB ought to be able to hack this, right? Sorry, this lecture seems to be very hacky. Let's see here. Ooh. Ooh. Cool. As you can see, there's something funny going on at y equals x, isn't there? Yeah. Ooh. Hey, fun. I mean, I could play with this all day, but let's see here. Well, anyway, I should tell you more about the geometry of differential equations. Here's a question. If you have a vector field, right? Say m comma n. Let's say p comma q, right? Like pi hat, q j hat in the plane. If you wanted to find curves which line up with the vector field, right? What differential equation would you solve to do that? How would you find curves which match p comma q, so-called integral curves? I'll talk about that probably next class. That's the next thing on my docket. So, not in my notes. It's in the notes, but I've grown to understand more about it. I think I lecture more clearly than the notes on this topic. I'd like to think that. Anyway, we'll start with the quiz, though. So what's the quiz on? separation of variables, exact equations, integrating factor method, and substitution type stuff. Yeah.